Alrighty, hello. So we're learning C++ for game development. The big thing of C++ is manual memory management. Now I know that sounds like fun, but don't worry, we're going to take it one step at a time. First thing we're going to cover in this video is more of like a C style, like raw pointers. So we're just going to start an empty project, call it whatever we want, that is fine. Okay, so let's say we want to work with some stuff. So we'll go make a class. Really doesn't matter too much. Okay, and then we'll make a program. Okay, so let's say we want to allocate like an array of things. So we can go with that, and we'll specify. Okay, of course we need malloc. So malloc is memory allocate is a kind of C standard function. So we will. Okay, now there's an issue with this, and that is that malloc generates a void pointer. We need it to be a thing pointer, but that's no problem at all. We can do a C style cast, and here it is. All right, so let's go through and print out the addresses of all these things. So we'll say okay, so remember, things is a pointer to a thing. And what we're doing is we're incrementing it. So we're going pointer plus 1, pointer plus 2, pointer plus 3. Or something like that. 0, 1, 2, something like that. Now, a pointer is just like a 64-bit integer or something, which indicates a position in memory. Okay, it points at something. It's the address for this thing. So I'll run this right now, and we get these. So this hex address over here is where the first thing is, and then as we step it up, it seems to go up by what? So this digit goes up by 1, so it goes up by 16 plus 8, so it's going up by 24 bits. 24 bytes each time. So the reason for that is that we know how many bytes are allocated to one of these thing instances, and every time we increment the pointer by 1, because it's a pointer of things, it's going to step up automatically by 24 bytes to get to the next thing. Now, it seems a little strange that it's going up by 24, right? Because an integer is 4 bytes. A double is 8 bytes, 64 bits. A character is 1 byte. So let's go with this. Let's say okay, well, that confirms our suspicion. Yes, it's 32 bits, 4 bytes, and yet the total comes up to 24. Why is that? So when we have a data type, because this is a 64-bit program, when we have a data type which is not really, what am I thinking? Different data types stuck together in memory, then they are promoted to 64 bits. In contrast, if I change all of this to int, because this is the same data type, we do not need to kind of promote them. We can stick it together. And similarly, Similarly, if we had them all as double, then what do we have? The first two would be 8 bytes each. And then because this is a different data type to double, it gets promoted by the compiler. So if we just get rid of that, we should have 16. Fingers crossed. Yes, we do. And also, side note, we can see that in our hex addresses, we're stepping up by 16 bytes each time. Okay, fair enough. So that's one thing we can do. And it turns out that also we can add functions. And they do not add to the data size. The functions are actually kind of stored away somewhere else. There's like a virtual lookup table for class functions. So the functions are not stored within the class, but they are declared within the class more or less. Okay, so this is cool. Again, what we're doing today is just getting a kind of raw feel for how this works. The next thing we can do is we can okay, so if you're coming from Python, class functions have like self. So that's fine. Who cares? That's fine. What am I thinking? Functions, the class functions have a self in Python, which is a reference to the instance itself. And the equivalent of that in C++ is this. This is a special pointer, which points to the instance that the thing is being called on. This is kind of equivalent to, I don't know. What do we have? We have, let's go void set A, and this works on something like this, right? Right, and this is exactly the same. Whether we have it declared inside the class or outside the class, it's the same stuff. Alrighty, so where was I getting at? So this malloc memory allocate basically allocates space in RAM to create these things, and this new goes ahead and creates one and returns a pointer to it. Okay, so I'll say that again. Memory allocates a chunk of space for things and returns a pointer to where that chunk can be located. And new creates something and returns the address that it was created at. So what we can go do is we can say, okay, we'll go the first thing of things, thing pointer, but then it complains and it says, hey, things, when we use square brackets to access, because this is a pointer to a thing object, then this expects an actual object, not a pointer to it. What we can do is we can dereference this, and this takes the actual stuff which is in this location. So it takes all that 24 bytes of data and copies it over to location 0 of that array. Okay, so then we can let's just print things out. Okay, yeah, so as you can see, when we are taking an actual object that exists, so we've got the 24 bytes of info, we use a dot to access its member, okay? But when we've got a pointer, we use this, literally looks like an arrow, to get in there and grab the data. Okay, let's just go ahead and run this. And yes, for both of these, the value is A. It's what we expect. So let's see what happens if we change it. Huh, alrighty. So originally they both had the same value. Now on the array, it hasn't changed, but in the actual location, it has changed. And that kind of makes sense if we remember that what we've done with this dereference is we have gone in, grabbed all the bytes of data and copied them over, okay? So when we change A, it will not update through the copies. So kind of a better way to deal with this is we'll make a pointer to pointers. Okay, let's go with this. So we want to make 3 pointers to things. We create that memory and we return where that can be located. So this is a pointer to the thing pointers. Okay. Now a pointer is a 64-bit address, so we would expect each of these to have 8 bytes. Let's run that. Yeah, that looks good. Okay, so we have thing pointer has 8 bytes, and as we step through this array, because this array is not storing the full 24 bytes for each of these objects, it's just storing an address where each of them can be found. So yes, we are going up in 8s. I guess we should be, what? Yes, that's hex math over there. Well, that's interesting. What do you reckon happens if instead of adding onto that pointer, we access it? Oh, I'm going crazy. You guys, you should have told me. All right, now let's do this again. Yeah, no, guys, I'm going crazy. All right, so thing pointer has 8 bytes, and yes, these are stepping up in 8 bytes. Okay. So, where were we? Well, what I wanted to do was, again, print out what's in each of these. Huh. That looks very interesting indeed. So the reason for this is that this is a pointer to pointers, but these inner contents have not been set. So these are uninitialized pointers, which means they have like a very meaningless default value. So what we can do is we can say right. So this is the memory location, and this is what's inside that memory location. That looks good. So yeah, each of these memory locations is 8 bytes each, and the object they're referring to has not been initialized. Okay. Cool. So what I'm going to do is, let's grab this again, and let's redo it. When we create things with new, we can free them with delete. Now thing pointer has already been declared, so we don't need to redeclare that. Data type, we'll go things to, and now we can just pass in the actual pointer. We don't need to. Okay, so now, again, what we're doing is we're taking the memory location, that's the pointer, we're copying the 8 bytes of that memory location, so we're copying the address over in here, and then when we change something and the memory address, these should both still be pointing to the same thing because they are storing memory addresses. Okay, that is good. That is good. All right. So there are some issues with pointers. One thing is it's a bit hard to keep track of everything where things should be allocated and freed and everything. And the other issue is the dangling pointer issue. Okay, so we get a memory leak. We get a memory leak if we allocate some space and then forget to free it. Because if we overwrite any of these variables, then we will lose the location where this thing pointer memory was allocated. which is fine if we're just doing a small program. If we're doing a larger program, that becomes an issue. But what I want to do is delete thing pointer and then look inside it. Alrighty, let's see what happens. So we delete a pointer and then we print out the pointer. That's interesting. Ooh, alrighty. So we've got something. Let's try this. Let's try. Okay, it's looking a little better. Okay, so things, the first element of things2 will be that thing pointer. So if we run this, we can see that they are both pointing to the same thing. However, the underlying memory has been freed, has become unallocated. So when we go and grab whatever's in there, it might be a weird result. It might throw an exception. It's really undefined behavior. So this is a dangling pointer issue where we've deleted something, but we still might accidentally access the underlying memory. So that's an example of some things we can do. There's a few more things we can do. One thing is we can resize. So we can say we want to make things2 a little bit larger. We use the reallocate. And what we do is we take in a block of memory, which is a void pointer. So we say things2, and then what I'm going to do is I'm going to increase my thing count. So what this does is it attempts to keep things in the same location, but just stick on a bit of memory at the end. But if it can't keep things in the same location, it will copy everything over to a new location in memory where I guess 4 spots have been allocated. And I think it's also good practice to cast this to a void pointer before we work with it. All right. And then the last thing we can do is we used malloc. If we want to delete something, we use free. So again, what am I going to say? With new will create a new pointer to a thing. We'll create a new thing, return its underlying pointer. Delete will free the underlying memory that this points to. Okay. Malloc and realloc are for C-style memory allocation, so it just allocates chunks of space that we can use, and free will free that space. Anyway, nothing too exciting, I just print stuff out. Hope you had fun, and yeah, that'll be it for this one. I'll see you in the next one. Bye.